This is the RoboMiner. Today we need to give it some audio. In the last video, using lots of off-camera details and ChatGPT, we started to pull together the concept of this little RoboMiner type rover to potentially be used in a game. We then ventured into Onshape to start fleshing out our structures, leading into the development of our first front plate with a little screen on it. We made some stuff, we continuously redesigned some stuff, we of course broke some stuff, but in the end, we got our first plate. In this video, we're going to continue the build by creating our top pyramid frame, where we'll briefly cover some designing for CNC considerations. We're also going to work on the plates and the electronics for the side speakers, where, almost predictably, we run into some problems. But not so fast. In the last video, I forgot to show you some important parts of the product and prototyping process. And as some comments pointed out, they wanted to know more about the functional drivers of the robot. So let's do that by considering the game that this robot is meant to be a part of. Firstly, let's understand what we know so far about the game. Remember, this is a concept, so there are no real low-level details yet. To begin with, let's pretend you're in your backyard or in a public park, for example. And you have our RoboMiner to hand. You come across a patch about 5 meters by 5 meters and you decide to mine it. The RoboMiner sets to work by moving over that patch in a specific pattern that you've trained it to do. Your RoboMiner stops because it's found a patch of valuable compounds. It needs to mine it. Now that you've found some compounds, you keep going to try and find some more. Your RoboMiner is connected to your phone, so when you're ready, you'll upload what you mined to the digital part of the game. Your compounds need to be refined so you can now sell it or trade it to make more virtual energy, which you'll need to power your RoboMiner in the first place. So given what we know, we can assume a number of functions for our build that we are going to need to figure out. It needs to move, but not as fast as a race car, for example. We are going to need to use GPS and probably a compass to detect the position and direction of the robot. The little screen needs to convey what state the robot is in. Has it found something? Is it mining? Is it being trained? We need some speakers for some simple audio cues for the user and for some personality. We also need some way for the user to train the robot to perform various types of scans. Okay, so we don't have all the details of the game just yet, and to be honest, when you're building concepts, you pretty much won't have all of those details at this stage, but we've got enough to move forward with. We know we need a robot, it needs to move relatively slowly, some simple functionality, that sort of thing. We can move forward using that information as the functional drivers. So the second thing that I forgot to mention is in these types of builds actually quite important. So my bad, and I'm sorry that I didn't show it. And what that is that when we create a concept on the screen, we really need something tangible, something that we can look at and play with and get a sense of the physics of what it is that we're building. And in general, this is called the junk prototype. This pile of absolute junk is actually extremely valuable, not in the cash sense, of course, but in terms of what we can learn about our design before we even get into CAD software. Okay, so making these types of models can actually be really fun. You can see I just pick up any old junk I can find around the house. It's mainly cardboard and blue tape and hot glue and chopsticks. Sweetheart, if you're watching this video, that's where the chopsticks from the kitchen drawer went. What can I say? Anyway, so what did I learn by building this model? So firstly, I figured out that this bottom section was and is totally wrong, way before I spent hours in design and or 3D printing to find out the same answers. It let me get pretty close to the wheel and tire dimensions. It let me think about the steering mechanics, the actual positioning of the wheels for the turning circles, for example, and it let me place them in a way to not make the concept so top heavy, but still provide the clearance, mining vehicles, top aesthetic sort of thing that we're looking for. The back wheels are in a direct line from the diagonal, which I think is correct, while the front wheels are too far forward. We're looking for a triangle here. So that's a lot of value for something that is really just junk. I actually took the measurements directly from this plate to start designing the top pyramid in Onshape. And so using that as a starting point, we get a good sense of scale and presence of the device. So speaking of Onshape, let's just jump back in there right now and take a look at the framing pieces. They're the next thing that's on the build list. Here you can see the original frame parts in our top pyramid studio. I want to turn off all of these components and concentrate at the moment just on this base part. This is the front edge. It's the part where the panel sits between these two faces. If we switch over to the top pyramid's side part studio, we can take a look at the plate design. If I zoom in to the bottom corner, you can see how the plate is essentially flat because the inner angle between these two part frames is at 90 degrees. We can make sure of that by coming back in and using this handy measure tool. If we select this face and this face, we can see here that the angle is 90 degrees and we get the visual indicator from Onshape on screen at the same time. Now, given that these parts of the robot are a frame that will contain the upper components, I'm thinking that I will want to make these parts out of something much sturdier than a 3D printed resin. And so I'd like to think about making this frame in aluminium, which means we have to think about how these parts could be made using a metal process like CNC. As it is, these parts are not designed for CNC, and because designing for CNC will change these parts dramatically, if we want to make future changes to the shape of the plates that fit into the frame, now is the time to do it. So now you're seeing the frame parts modified for CNC, along with some additional framing structures on the back of this base piece. You can also see how different these existing plate faces are, with this curve added in. And that's because we need to consider the likely tool used by the CNC machinist to make our part. Designing for CNC requires us to consider how the parts can be made from a single block of aluminium. And that is why you can also see this part now has very large 90-degree faces. But in modifying these areas, it also means our plates have to change to fit. Because our plate is based on the frame, we need to change it as well. So you can see, just by changing something small, like a round needed for a CNC, that several parts could also then need to be changed. All of these changes can take a lot of time and cost a lot of money. Certainly if we are making changes in the CNC parts each time. So how do you design for CNC? It's really a big subject and one that takes a lot of time to get your head around, but documents like this one from Exometry can really help you understand what design changes are needed to make CNC possible. These types of charts can give you a lot of valuable information to help get your CAD designs in a good place. But at the end of the day, CNC machining is an art form, and working directly with your machinist will help you understand their requirements the best. I've attached a link to this document in the description below. Okay, so we might as well get on with designing the speaker side plates while the frames are printing. Here is our little speaker. We're going to have two of these. They're pretty cheap and nasty from a company called IEMA. They are, I believe, 2-inch, 4 ohm and 5 watt speakers. I'm not expecting very high quality or even high volume out of these speakers, but they should be just about right for this prototyping type of level. First step to designing the plates is that we have to recreate the speaker for us to model against. Like our previous process with a little screen, we first need a simplified model of the speakers with accurate external dimensions for us to model the plates and speaker holders. Okay, so we've got our speaker done, and now we can concentrate on creating a housing for it to sit in. One of the real challenges with this particular speaker is you'll notice that there's no real place for anything to grip on. It's got this very, very small shelf here, about 0.5 millimeter, that is sticking out, and that's what I'm going to use as the mechanism to sort of snap the speaker in place. So what I started to do first was design this top inner cap. You can see that it's sort of designed to snugly fit the speaker right up onto the black part. If I come over here, I can turn on a section view, and I think we can grab that. And you can see how that's being designed. It's pretty close in terms of the gap and the edging. We've got to enable, or we've got to allow for shrinkage and or expansion in our 3D printed resin. So that's why I'm allowing these gaps to sort of make up the space. You can see on this side, in fact I've cut it off, but there is a cutout on this side because the speaker itself has the little edges for the wires to attach to, and we want this to be completely unintruded so the wires can freely move down into the carcass of the pyramid itself. Let's turn that view off. You can see that it's also sort of shaped at an angle, and we've got this deeper trough. So the idea was that we can create a top plate that sits on top, and we screw down through this top plate to secure not only this top inner cap, but also the speaker itself. Let me hide some stuff. I'm going to hide that plate. And you can see here now, this is obviously the top pyramid with our speakers, but you can see here that we have a different color for our plate. Now, let me hide some of these things away. So you can see our speaker is here, and it's designed here because importantly, we need to take our frames into consideration. You can see they're resting right up against it. If we didn't apply what's called a Boolean modifier, let me move that over, then we would actually hit these frame components. Now, that's not going to happen to us, and the way that I can tell you that's not going to happen is again from another really cool tool where we can call in interference detection. This is going to let us select two objects or more, and if they interfere in some way, it will show us. It'll show us in bright red that the components are going to hit each other. It's not happening here because I've actually created a Boolean modifier and used it as a subtraction. Let me just hide this bottom frame, and you can see here on this component that we have an accurate Boolean removal of the part where it's going to sit on the frame. It's the same on the other sides as well. If I hide this one, you can see there's just very small locator sort of areas for this component to sit against the frame. Before we jump out of here, this is Onshape in dark mode, which is in beta at the moment. I don't mind it, but how does it look to you on the screen? I know sometimes dark mode can make it difficult to pick up certain details. Let me know down in the comments if you want me to keep using dark mode or stick to the normal white background. We'll get on with making some side plates and taking a closer look at our frame components. They look awesome. while everything is printing out, I want to make a start on the electronics. Now, I've thought a lot about how I want to show electronics on the channel, and my goal really is to take away the complexity at the beginning for those that are just starting out. And I understand it can be really overwhelming. The secret to working with electronics is pretty much like everything else. We just start at one part at a time, one piece at a time, figure that out, and then move on from there. Now, the circuit I'm about to design, I'm sure a lot of you already know how to prototype. But for those people who don't, I want to go through a really high level understanding of the components, how we're connecting them up. Now, we want to use multiple speakers and have audio files playing, but there's a challenge with that because we need somewhere to store the audio files that we're going to be playing. And in this case, we're going to use an SD card to do that. So we want to concentrate as one component on the SD card first, and we want to make sure that it works 100%. So moving forward, when we're working on any other type of circuit, if there is a problem, we want to be able to remove the SD card and that circuitry as being anything to do with the error itself. Here again, we're using an ESP32 S3 dev board and a micro SD card adapter module, which of course we also need an SD card to read from. As I said, this is really high level, so I'm not going to explain what wires are connected to what pins here. The purpose is to show people that may be a little intimidated by electronics that we really only need to connect up 6 wires. And 2 of those, the red and the black, are for power. Shortly you're going to see the actual circuit board, and there's wires and stuff everywhere. But again, all you've got to think about is those 6 wires that made the connections. Now, there's a lot of great YouTube channels out there that go into the detail of this stuff. And one in particular, there's another old man, and I'm pretty sure Bill would be okay with me saying that, but he's got a great channel that looks at this particular circuit in detail. His YouTube channel is called DroneBot Workshop, and I'll leave a link in the description below. Now, we're going to move into code, and just like electronics, I don't want to go deep and dirty into the coding level because I don't think a lot of people want to see that from this particular channel. But what I do want to show is maybe some really important things and give you a bit of a look into how I write my code and the level that I go to when I'm making these projects and the mindset behind why I do it. One of the biggest issues I see with video tutorials on coding for microcontrollers is that a lot of bad habits come from simply following the same code as someone else has produced. An example of that is on the screen I'm showing you with a very simple piece of code designed to check our SD card. The problem with the code is that while it should perform the check, it really is very poorly written code, breaking all sorts of conventions and standards that as developers or makers, we should really be trying to build towards. For example, if you've never seen this code before, what do the numbers 12, 13, and 11 mean? What's that order got to do with it? And what does CS stand for? And I get it. You're in a rush and you just want to make something and get it working. But here's the thing. I just spent the last couple of minutes telling you how important the SD card is for not just this project, but other projects moving down the track. So it stands to reason that we would take longer and put more effort into making our code as good as we could for this particular part. Believe me, issues with reading and writing data from and to files on things like an SD card can lead to some hideously frustrating issues down the track. So we really want to make this right. Now, I'm not going to go through this line by line, but you can see a difference here. The other code file was about 30 lines long, and this file is about 180 lines long. The amount of code is in no way an indicator to code quality, so don't make that mistake. But what is important here is that this code is very clean, very well structured and documented, meaning I can come back in 6 months' time and understand what is going on, or someone else on my team will know what the purpose of the code is. Probably more important is that it is robust and reliable against a lot of the known issues we could run into with flashing code up to chips like ESP32s and Arduinos, for example. It performs soft resets of the board to eliminate flashing issues. It tracks those resets with non-volatile memory to ensure the same errors are repeated. It fails gracefully when it needs to, and it succeeds clearly when it does. We can see this failing 3 times in a row, exactly as it's designed to do. Our solution is broken, but there is no confusion about how. The error code here is showing us that the SD card is not formatted, so let's fix that. We need to use a little application called Rufus to format this card, because the SD card reader needs it to be formatted specifically in the FAT32 file system. And unless you're running the very latest versions of Windows, generally it can't handle an SD card above 32 gigabytes. I'll leave a link in the description for Rufus, but we're looking for the P for Portal version. Download it and plug your SD card into your computer. We need to make some important settings here. Make really sure you are selecting the right drive specifically here. You can see this is new and has no label. In boot selection, we change to non-bootable. We leave the partition scheme set to MBR. We give the card a name. And here we make sure we select the large FAT32 option. Click Start and agree to the warning, and it should only take a few seconds to complete. Now it's just a matter of putting our SD card back into the module and holding down the reboot button on the ESP32. As you can see, super clean, telling us there are 0 restarts needed, the card initialized, and is ready to use. Now we're ready to hook up our audio amplifier and a speaker. We're just going to hook up one speaker and one amp to begin with. If we get that to work, hooking up 2 is pretty simple. It's all the same wires hooking into each other. So like before, without the low-level details, let's take a quick look at how this circuit sort of extends on what we've just done. As with our last hookup, we've got our ESP32 and our SD card in place. Now we need to add the audio amplifier, which is a Max 98357 I2S or I2S 3-watt Class D amplifier. To power this, it needs a 5-volt input, and the ESP32 board that I'm using does not output that, so I need to hook up a separate bench power supply. And lastly, we of course need our speaker. So to wire this up, let's think about the power first. The Max is taking power from the bench supply, and the ground is common to everything. So we just add it to both the Max and to the back of the SD card as well to share. We then need 3 wires from the ESP32 to the Max, which send the signals and select it as the output device. We have 2 additional specific wires. One is the amplifier gain, which we tie to the ground, and the other wire needed determines if we're playing audio on a left or right channel in the case of stereo. For now, we'll just route this to ground to give us a left channel. So the first step in just hooking up a single speaker went okay. Now, as could be expected, the audio quality is pretty terrible, but that's okay, it's exactly what we need. I really wanted to just crack on and hook up the second speaker, and it's right about here that things started to get a little bit spicy. Now, it really doesn't help that I'm partially deaf in this ear. I mean, I'm old, this is the sort of stuff that starts to happen. But even with that, it became pretty clear pretty quickly that there was something wrong with one of the speakers. At this point, you need to stop and run through a basic type of checklist, starting most obvious first and eliminating things as you go. Remember that I said the SD card is bulletproof. So great, we've got a problem, but we can remove that entirely from where is this issue occurring. We start very simply at the very basics. We start checking wiring, double check it, triple check it, see what's happening. We had audio playing out of one speaker but not out of another, so simply switch the speakers over. And that's what I did. That's what I could really quickly determine that the issue was actually in one of the speakers, not in the rest of the circuit. Time to pull out the multimeter and start checking to see if there is something wrong with the speaker itself or just the wiring. And using this very basic but awesome tool, I was able to determine that the wire itself was the issue. That's really unusual, but this shows you that it can happen. There's no split in the wire, it's just got to break somewhere. I soldered on a new wire, I obviously checked it, and it's time to see if our little droid audio works. Awesome, that works. Whew. But now I'm on to the part that I actually really enjoy doing the most, which is bringing all of the parts together, from the frames, the electronics, everything, bringing it all together for the very first time. Right, so I'm really pleased in how that all came together. Now, obviously, I printed out a couple of just sort of blanking plates for the back and the top, and we'll get on to those panels in due course. All right, so in the next video in this series, maybe I want to switch it up a little bit and start to have a look at the wheels and the motors that power them, and maybe even the frame sort of holding it all together. As for right now, I'd really like to take the time to say a massive, massive thank you to everybody that watched the last video, and especially to all of those people that reached out in the comments. People were kind and courteous. It was so humbling, and I I really can't express how much I appreciated that engagement with you guys, which was wonderful. People reached out for, all sorts of things, advice and help and things like that. And one guy in particular named Sion from Unexpected Maker, without anything in return, he just reached out and said, listen, I've got some components that I'd like to send you because I think they'll help you out in the projects that you're doing. Now, I was absolutely blown away when this box of components turned up, not just because he'd sent me so many components, but the quality of the components. They're so beautifully produced and put together. I can immediately see how much time and effort and care that Sion had put into producing these components. His website is fantastic in terms of documentation, the details, high-res pinout documents on electronics, fantastic. And so that's why I have no hesitation in showing you these components, and I really look forward to using them in our future videos as well. Thank you so much, Sion. I really appreciate it. Now, as I said, lots of people were positive, and they just gave me so much motivation around this, and there was great constructive criticism as well in terms of how to possibly make these videos better. Now, clearly that's something I want to do. So after Christmas, New Year, I took a lot of time and just sponged in, grokked as much stuff as I could around making better videos. And that's everything from lighting to audio, blend selection, all of those things. I started to learn motion graphics, right? Now, you've seen it in this video, so go easy on me, right? You know that it's going to take a while to get better at this sort of stuff, but that's what I'm trying to do. I'm trying to really put it all in there to make a better video for you. So please stick by me as I learn here. All right, you all know what to do, to help the algorithm out, of course, as well. It'd be wonderful to see those comments again and to engage with you guys further. If you like the video, a thumbs up, you know the drill. And if you're not subscribed, well, what are you waiting for? Just help me out, jump on the subscription and jump into the comments and say hello. All right, I'm the Old Man Maker, and until next time, take care.